Okay. Oh, sorry. Okay. Apparently, we're still figuring out where classes are. That's not good. All right. So today we are going to further talk about threads and their implementation. So this should help you understand Lab 2. Quiz 1, I still don't know what it looks like. So in a lot of ways, we're ahead of the other class. So we're at least 2 lectures ahead of them, minus some other stuff. So if you look at, on Ashvin's slides, there's some questions at the end. That will probably look like the short answer part of it. I looked through them. We can answer pretty much all of them, I think, except for anything that has to do with an MMU. We don't have to know that, because that's how you actually implement virtual memory, and we'll see the entire implementation when we talk about virtual memory. Yeah.
So preparing, go over the questions off of his slides, and then the rest is just multiple choice?
Yeah, the rest is multiple choice or true, false. Probably be conceptual stuff, like system call stuff, threads, processes, what's an address space, stuff like that. Yep. Some thread stuff will be on, but not like super implementation detail. So like you should know, because what we're going to talk about today, we pretty much already talked about with processes, like context switching and all that, so we'll see. So all that stuff you should know. Yeah.
Is it open book or closed book?
It's online, so how am I going to stop you?
What does that mean? So
It's open internet.
okay.
I mean, I'm not going to, yeah, I'm sure the TAs aren't going to watch you or do anything. So I don't know how on earth you would stop someone, so. Okay, so let's talk about threads implementation. So there's a few multi-threading models that you can take when you're implementing threads. And the question pretty much lies in where do we implement threads? We can either implement them in user space or kernel space. So what you'll be implementing in Lab 2 are user threads. So they are a complete construct only in user space. The kernel doesn't know about them, hence their name user space threads. So the kernel doesn't treat your process any differently. According to the kernel, you have a single process that has a single thread, and what you do with that single thread is completely up to you. So if you want to put threads on top of it, which is what you'll be doing in Lab 2, you are free to do that. But kernel threads, on the other hand, are implemented completely in kernel space, so the kernel actually knows about them. So the kernel manages everything for you, so it allocates the stack for the threads, which is what you'll be doing in Lab 2, and will take care of all the context switching for you, because essentially it can just reuse all the process context scheduling, because it's the same thing, except it has to do even less. So it just has to swap the registers, which would also swap the stack, and that's it. It doesn't have to change the address space or anything like that, because we all know now that threads are in the same address space as the process. So, yep.
So you said it manages the stack and the program pointers?
Yeah, and all the registers. So it's pretty much the registers, which one of the registers is a stack pointer. So every thread needs its own independent stack, so it can go ahead and execute, normal C code and be independent from each other for only executing code. Other than that, right, it shares shared memory, so they can see the entire heap. So no matter where threads are implemented, there's going to be a thread table somewhere. So it's similar to a process table, except it is less information, because a process table will contain, all the registers and stack, which is what a thread is. It's just like a subset of a process, because the process also has the address space information, all the memory, the open files, everything kind of related to a running process. So this could be in user space or kernel space, depending on where your thread support actually lives. So for you, it will be in user space, but there are kernel threads in the Linux kernel, so there are some section of that dedicated to storing information about threads. So unfortunately for you, for user threads, there also needs to be some type of runtime system to determine scheduling. Thankfully for you, at least in Lab 2, it's going to be quite easy because you're just going to have a queue of threads that want to run, and they're going to request to run, and then you just serve them in order. But yeah.
Sorry, what is the process table? I know you said you saw that, but I kind of don't remember it.
So a process table is just all the information associated with a process.
But is it like in hash table format or?
So it's just a big structure.
Okay.
So yeah, it was in one slide that pointed where in the kernel tree it was. It's like it's called a task struct, so it contains all the information about a running process. So it has all the registers, it has scheduling information, or memory information, open files, and remember the process control block? Yes, the process control block? To a certain degree, okay. The process table is just a bunch of process control blocks. So that's how you keep track of all the running processes on your machine. Okay, so if you have user threads, you have to determine your own scheduling because you can't rely on the kernel. It will schedule your process, but you have to determine which of your user threads runs at any particular instance. But in both models, threads live within a process. So you could avoid system calls. That's one of the benefit of doing user level threads, which especially was a benefit back in the day when you only had a single CPU anyways. So you can avoid system calls because it's actually quite slow to transition from user space to kernel space, have the kernel do some stuff and then transition back from kernel space to user space. So for pure user level threads, you don't have to do any system calls. So they're going to be very fast to create and destroy. And there's no context switches that happen within the kernel. You, of course, have to do your own context switching, which again is Lab 2. But the drawback of this is that according to the kernel, your process only has one thread. So if your current running like user level thread hits a system call, your entire process is going to be put to sleep while the kernel goes ahead and resolves that system call. So any of your other threads aren't going to be able to run. So by having user level threads, you will not have any parallelism whatsoever, right? Because it only will execute a single thread. So you can do things concurrently with just a single kernel level thread, but you can't do anything in parallel without the kernel's support. So for kernel level threads, they're going to be slower because creation involves a system call. But if one thread blocks, the kernel actually knows about them and knows they are all independent streams of execution. So if one of your thread blocks or is doing a system call, then another thread can be scheduled to run while it's waiting for that one. So, and again, if you have 8 cores on your machine, for example, and you have 8 threads, it can go ahead and schedule them all in parallel because it knows about them. But all threading libraries will at least have some user code. So the pthread library that we saw before, that has some aspect of library code that will kind of see what it does. And we'll see through the magic of strace what system call ptrace actually uses, pthread. So the thread library is going to map user level threads to kernel level threads, and then there's different ways of kind of breaking this down. So what you'll have in Lab 2 is called many to one. So many user level threads are going to map to one kernel thread, which means your library completely exists in user space. So again, as far as the kernel is concerned, you have one running process, which of course just has one thread. In the one-to-one model, one user level thread corresponds to one kernel level thread. So that means the kernel handles everything. It does the context switching for you. It does the scheduling for you. But of course, you're at the mercy of the kernel as to when your thread actually runs. And then there's many-to-many, which is kind of weird and is something they did in the past that's not really used now. It's a bit complicated, and we'll see kind of a better way to do that. But many-to-many just means that many user threads can be mapped to many kernel threads. It's not exactly a one-to-one correspondence, and it's not exactly a many-to-one correspondence. It's somewhere in between. So the many-to-one is a pure user space implementation. Again, this is just lab 2, so there will be no system calls. You will be managing everything yourself. So it's going to be fast, and it's going to be portable because it is purely written in something like C, which is basically just portable assembly. And you're not depending on any system calls, so you can reuse it on Windows, you can reuse it on Mac, Linux, doesn't matter. It's a pure C implementation of threads. And it's just a library. But drawback is, again, that if one thread blocks, then the entire process is going to block and another thread can't make any progress. So it can't do anything in parallel because, again, the kernel only sees a single process. So back in the day, this may have been good when we only had a single core on our machine, but everyone probably has at least 4 cores on their machine. So this probably isn't a good thing to do anymore, although you still get to implement it. So one-to-one just uses a kernel thread implementation. So there's just a thin wrapper around the system calls just to make it easier to use. We'll see that the system call is kind of weird looking, and it still has to allocate some stack space. So the kind of pthread implementation is going to malloc a thread for the new kernel thread, and then essentially tell the kernel where that address is, and then the kernel takes care of all the scheduling and the context switching, and which would be swapping the registers and everything like that. So this is the way to exploit the full parallelism of your machine, because the process or the kernel has full knowledge of everything, and it can schedule all the threads to run as it wants. But again, this has a slower system call interface, and in very, very niche scenarios, you might want to control the scheduling yourself. If you have threads that maybe have higher priority, or you know one always needs to happen before another one. So you essentially give up that freedom of writing your own scheduler by just using the kernel scheduler. But thankfully for all of us, the kernel developers are quite smart, and the scheduler is quite good. And this is the actual implementation typically people will use. And for Linux, with pthreads, this is the actual implementation. So the many-to-many is a hybrid approach. So the idea is that, well, I might want a lot of user-level threads and more of them than kernel-level threads. So if I only want to ensure that I have parallelism and say each thread is really, really expensive to create, well, then I'll just create the number of kernel threads equal to the most parallelism I can get out of my machine. So if I only have 8 cores, I'll create 8 kernel threads, and then I can put like 10,000 user level threads on top of that, since they'll be cheap. So the idea is to kind of get the best of both worlds there. So you want to get the most out of multiple CPUs and also reduce the number of system calls. But however, this kind of leads to a more complicated threading library. And then depending on your mapping luck, you may block other threads by accident, since again, the kernel doesn't know about them. So you still have that same issue. So if you map, if you have tons and tons of user level threads and you map 100 of them onto a single thread, and they happen to all contain blocking system calls, well, the kernel can't schedule between those because, again, it can only schedule what it knows about. And it makes things very, very complicated, and we'll see just a technique that kind of uses this idea, but is a lot easier to implement. But the threads get to complicate the kernel and make our life difficult. So the question is, how should fork work if I have a process with multiple threads in it? Right? It's kind of weird. If it's an exact copy, should it be like an exact copy and copy all of the threads? That would get out of hand very, very quickly, and also make a fork bomb with threads very, very effective. But so the way the Linux kernel deals with this is that Whenever fork happens, it will create a new process like fork does, and that process will only contain a single thread, and that will be the thread that called fork. So that way you avoid some potential issues of if you fork, right, it's just a snapshot at that point of time. And if there's multiple threads running, they might be playing with memory and like kind of halfway in between some operations. So after the fork and you have two processes that are now independent, and then one only has a single thread, it might be in some weird undefined state because some other threads were monkeying around with memory at the time of the fork. So, yeah.
But if you had, like, say, 10 threads on one process, and the process was just kind of like a loop with a fork in it, wouldn't all of the threads, all 10 threads, eventually get to that fork line?
Yeah, so the question is, if I created 10 threads and within the run of all those 10 threads there was a fork, so if that happens, this rule still applies, but it would create 10 new processes, and then each of those new processes have a single thread, which would be a copy of whatever thread called it. Right. So good question, and we could fork bomb ourselves even faster if we just had our loop inside of that. Yeah, so that is like a really hard thing. So there's also this code that we won't cover in this course, but if you ever find yourself forking in a thread, you're going to find like weird inconsistent state, but you can use this thing called pthread at fork to control what happens when a fork occurs so that you can leave your memory in some consistent state before the fork so that both the new process will have at least some consistent view of memory. But that's not going to be covered in this course. You don't have to know about that. That's kind of just a fun thing. I've never had to use it, thank God, because that would be awful. Oh, yeah.
Yeah, on the previous slide, what does it mean that pthread exit has status 0?
Oh, yeah. So that new process would be a single thread, and it could be within our run, right? That normally implicitly calls pthread exit, or you could call pthread exit. So because it's the only thread now, if you call pthread exit, it's going to end the process. And by default, it just always returns error code 0. But in the new child process, you could, of course, just call exit yourself and return whatever error code you want. Okay, so signals are our other fun complication. So if I have a process with, say, 8 threads and a signal gets sent to it, well, what happens? So what Linux will do is just kind of pick a random thread and have that thread handle the signal. So this makes concurrency kind of hard. So you have to consider any thread being interrupted at any time to run your signal handler code. So you don't know if it's the main thread, you don't know if it's a thread you create, you have absolutely no control over it, and this kind of gets very hairy. Yep.
Does it just pick like the active thread at any given time?
Yeah, so it would pick a running thread if there's one running, or one that could run if others are blocked. So
is there any way to politely suggest that it gives the signal to the main thread?
the question is there any way to politely suggest that it gives the signal to the main thread? Not as far as I know. There's other ways around it that will come way later. So you can kind of force the issue on that, but I don't think through the default signal stuff that you can do it. But you don't have to worry about that until Lab 3, where you actually have to deal with signals. But the nice thing about signals for you in Lab 3 is you have user level threads, so you only have a single process, so you know that your one process is going to be the thing that gets the signal. So it's a bit nicer for you. Okay, so this is the kind of default thing, instead of having many-to-many, one common technique is to use something called a thread pool. So if the goal of many-to-many was just to avoid creation costs, well, I don't have to support many-to-many in my threading library. I could have a thread pool, which just creates a certain number of threads and a queue of tasks. So maybe, like I said before, you want to get the most parallelism you want, and you would just create as many threads as CPUs in the system. And then as requests come in, you would just have a thread wake up, then give them some work to do, and then as soon as they're done that work, they'd go back to sleep, so you wouldn't actually destroy it. It would just go back to sleep, and then when there's a new task, it would go ahead and do that task. So you only create your threads once, you reuse them over and over again when there's no work to do, and that's one very common technique, and that's called a thread pool. So you might encounter this with one of the labs way later in the course. But since you'll be implementing many-to-one, our process lifecycle still applies, because essentially, your thread is just the virtual CPU, it's the actual execution of this. So this is your state diagram that all of your threads will be using. And then of course, since this is this is all user level threads, below this, because it's all running in a process, this also happens at the process level, right? So if it takes a system call, if it does a system call, then the process will be blocked, and then your threading library will have no idea that a system call is being executed. It would just consider it as running. So the code you have to implement in lab 2, you'll have to create a function called thread create, which essentially will create a thread, allocate some stack space, initialize some structure that will hold all the registers so you can context switch. And whenever you're done creating a thread, you can just have a double-ended queue that is just full of threads that are waiting or that can execute. And whenever you're done creating a new thread, you could put it at the end of that queue. And then as part of your scheduler, which is not going to be terribly sophisticated, your scheduler is going to be responsible for taking tasks from waiting to running. And in that case, the easiest thing to do is just to pick a thread that is at the front of the queue, because you can just assume it's like a line at Disney World or something like that, and it gets to ride next. So that would be the thread to run. And then in lab 2, remember we had cooperative processes or cooperative scheduling. So you'll have the same thing in lab 2. You'll have cooperative threads. So the only way for a thread to give up the CPU is that thread has to explicitly call thread yield, and that will transition that thread from running to waiting. So it'll essentially just put it back to the end of the line, so that, yeah, it'll put it to the end of the line, and then your threading library would just pick the next thread to run from the front and start running that. Yep.
You said when you want to save the state, you save all its registers.
Yep.
Is that kind of the same thing in user space, or is that only really in kernel space?
So it depends where the context switch is happening. So in our case, we're doing user level threads, so you're going to have to do the context switch yourself. But there'll also be, there'll also be another context switch under that, because the process the kernel knows about will be context switched in and out too. Yeah. Yeah, so you're essentially just creating fake threads, right? So thankfully, you don't have to take away the CPU from any thread in lab 2. They have to essentially relinquish it by using thread yield. But of course, any thread can just not call thread yield until it is done, in which case it would just hog the entire CPU. So the other transition you'll have to make is from running to block, and then you implement something called thread sleep, which just basically makes a thread not runnable anymore, so it can't be transitioned to the running state. And then eventually some other thread will call thread wake up, which will just put it back into that waiting queue at the end of the line again. And then you'll have to implement, of course, thread exit, so the running thread can call thread exit, which would essentially turn it into a zombie thread, and it would be terminated at that point. And I don't think you have to implement like a thread join as far as I know. There's a thread destroy, but there's no join. Okay. So like I said, the scheduler can just be some simple round robin thing. So you just create a queue that always runs the thread at the front of the queue. And then when it yields, it just, or a new thread's created, it's just always added to the back of the queue. So you'll have to do the context switch, and again, you'll have to save the registers. The first hurdle you'll probably encounter is saving the program counter. You have to monkey with it a little bit and kind of really think about it, because otherwise, if you save the program counter at the state it's at, it will go ahead and whenever you restore it, it will restore it to right before it saved itself, and it will just save itself again, and you'll get into this very nasty loop. So that's one thing you'll have to be careful of. And again, these are cooperative threads, so they have to play nice. And in lab 3, you'll do the preemptive version where your threading library will actually steal CPU away from a thread and force it to context switch.
So you were actually accessing like the individual registers within C in this case?
Yeah, you'll be saving them. Yeah, and creating a stack. Okay, so, yep.
So when a thread is running, what's the difference between putting it to sleep and then calling yield?
Okay, so that's a good question. The question is, when thread's running, what's the difference between sleep and yield? The difference is that if you yield, it will just go back to the waiting task and it could be run immediately again. It's still eligible for being run. While if you call sleep, it's in this block state, and block just means it's not eligible to run. So even if the CPU is idle, it still doesn't run. So of course, you can think you can brick your process if every thread goes to sleep and it's all blocked, then you can't make any progress anymore because no thread will actually wake up. Okay? All right, yep.
If the thread is blocking itself from running, how will it know when to unblock itself? Or does somebody else set that thread's block state to something else once it gets
Yeah, so the question is, if a thread puts itself to sleep, how does it get unblocked? And the answer to that is another thread has to wake it up. Yeah. Because otherwise you can't run again, so you can't wake yourself back up. Okay. All right, well, let's get into our next fun complication then and kind of review threads a bit more and just play around with them. So we'll create a program that spawns 8 threads, and each thread will increment a value 10,000 times. So if the initial value of that variable is 0, what should the end result be? 80,000, but not, right? So we'd expect to see 80,000. So let's go ahead and kind of practice some more threads and see an actual bigger join example. So here's my main. In main, I create an array of pthread types, which again, processes and threads are kind of analogous to each other. So if it's easier, you can think of that pthread type as just a thread ID, just like you'd think of the return value of fork as a process ID. So if that's easier, you can think of this as a thread ID. So I declare an array for all my threads that has space for num threads, which in this case is 8. And then I have a for loop which goes ahead and creates the 8 threads and gives it the memory address. The second value is null, so they're going to be a joinable thread because that is the default value. We're going to have them all run this run function, and we're not going to pass an argument because we don't care. Yep.
So in this case, by the end, you'll actually have 9 threads. You'll have the main one that's creating all the threads, and then you'll have the 8 threads that you created to run.
Yes. Yeah, so that's a good point. He brought up the point that in total, right after this point, I will have 9 threads because again, a process is going to be created and there's going to be a thread that runs main. So main will come here and then create 8 more threads. So in total, I will have 9 threads And that is such a good question, it will probably be on the quiz. If the other class knows that by now, which they might not. Okay, so anyways, let's see the run function. Oh, first, to start off, who knows what this static means? Because yeah.
Yeah, so it's basically a variable that retains its value no matter what the scope is.
Which sounds like a,
Global variable.
yeah. So what's the difference between this and a global variable?
I'm not sure about that.
Yeah,
Is that you get a unique copy of this in every translation?
yeah. So basically, without getting into compiler nonsense, basically this is a global variable, right? This line. And if you put static in front of it, it still behaves as a global variable, but you can think of it as you can only access that global variable from this C file, and you can't access it from another C file. So it's kind of like a global variable that other people can't monkey around with. So you're reasonably sure that it won't change out from under you. Okay, well, to make that even worse, so int I, that is a stack variable, right? It's just allocated on the stack. Who wants to tell me what that means?
Oh god.
What did they teach you in the C course?
Nothing.
All right, they taught us nothing in the C course. So in this course, right, knowing what's on the stack and what's in the heap and what's a global variable is kind of important, especially if we're in the same address space and we can monkey around with things. So annoyingly, so everyone agrees this is on the stack, yeah? So this essentially makes it a global variable. So it will be a global variable, and the only distinction here is that you can only access that global variable from within that function. But otherwise, it behaves exactly like a global variable. So if I did this, it would exist for the entirety of the program. But because this is now threads, each thread would use the same variable, since that's a global variable, and we'd have a disaster on our hands. Yep.
So, global variables are sort of a heap, or?
So global variables are stored when you load your program. So they're just, as part of some information, the elf file, there's going to be a section that has a data section that says, you know, X should go in this spot of memory, and it doesn't change throughout. So it lives as long as the process lives. So it is neither in the stack or the heap. It's just in some predefined memory space, and that's it. Yep.
So you mentioned that the static in I is a global variable. So say its initial value, like after some process, its value becomes 10.
Yeah.
So if another thread tries to run this function, will it be using 10 or will it be using any other value?
Yeah. So the question is, if some thread sets this variable to 10 and then another thread tries to read it, what will it get? And it will get 10 because it is a global variable. So it's just got one single memory address that it points to. The memory address will never change. And whatever the value is, because all the threads are in the same address space, they'll all get the same value. Yep.
Just actually with the static keyword, if we try to access this I in main, it won't work.
Yeah. So in this case, static int I can only access this I within this run function.
In the scope of this, like,
Yeah, within the scope of this.
this function.
Yep.
It's outside in the scope of the file.
Yep. Okay, so someone should have taught you that in the first year. Because now, maybe it didn't really matter back then, but now it really matters, right? Because if I change it to static, every thread can see that, and if every thread's going through this loop, I's not going to increment sequentially. It's just going to be like just random values all the time. They're going to fight with each other, and it's going to be terrible. All right, so in this case,
Wait, should you change it back then?
I did. Int I.
Oh, okay.
Yeah, this one,
I was looking at counter.
oh yeah, counter I want to be global variable because we're going to see the fight. Okay, so then after I create all the threads, I would join them because I want to wait for all of them to finish, right? And I actually care about when they finish. And then after they all finish, then I can print my counter and be sure that all my threads have finished execution. And this is a case where you would want joinable threads. Because if I had detached threads, what would probably happen if I just had detached threads?
One thread finishes and everything else dies because the main, because the first one returns and then the main gets returned and then everything else gets.
Yeah. So if I just have a detached thread here and then print counter, it's just going to rip through it. It's going to create all the threads and then immediately just print that and then exit the process, which will kill all the threads. So likely this counter would be some low value because some of the other threads might not have even run yet. And then main would exit and the process would die. Yep.
Pthread join is like wait, it's not pull, it just like stops this thread until it gets it. Or...
Yeah. So pthread join is the exact same thing as like wait PID. So it's going to wait for that thread to die. The main thread is going to be blocked until one of the other threads dies. All right. So anyone tell me why I wouldn't do something like that? Why do I have 2 for loops? Why don't I just, oops. Anyone want to guess why I don't do something like that? Yep.
You said you wanted them to fight, so you're trying to start all of them together and then wait at the end for all of them to
Yeah.
join.
Yeah, so in this case, I want to give the kernel the opportunity to parallelize this as much as possible. So if I have something like this, it's going to create a single thread, then wait for it, create a single thread, wait for it to finish, create the next thread, wait for it to finish, create the same thread, wait for it to finish. So I'm essentially just having only one thing is executing at a time. So I basically just made a single threaded program with a lot more steps. So if I do this, I create all the threads. So now at this point in my program, I have 9 threads, right? The main thread and then the 8 other threads that I'm hoping that the kernel will schedule nicely for me. And then they start dying off at pthread join because at this point there would only be one thread and it would be the main thread. Yep.
If pthread 0, for whatever reason, decided not to want to exit yet, and all the other threads exited, that for loop would have to wait for pthread 0 before it finished, right?
Yes. Yeah, so the question is, what about if pthread 0 exited, took way longer than all the other threads? Well, pthread join the first time it goes through this, it would wait on thread 0. So even if the other threads are done before, it would have to wait to join on that specific thread to clean it up. They'd all be zombies, right? So we just have 7 zombie threads until the first thread finishes, and then we just wait on, or essentially just wait on all of them. Yep.
Is there a way to communicate that you want to wait on all threads simultaneously instead of waiting for one and then the next and so on?
Yeah, so the question is there equivalent of wait where I just say I don't care what thread finishes first? Just wake me up whenever any thread finishes. And the answer to that is by default, no. So there's a non-blocking version of join, so you can probe its state to see if it's a zombie yet. So you could do that, but you'd have to poll and ask every thread over and over again. But as far as I know, there's no equivalent of just plain wait on anything. Okay, so now we get to run this. So if I run it, I'm expecting 80,000. And of course, when I run it, 77,000, not bad. I can run it a few times, 72, 57, yikes, 60, 66, 50, oh, we're getting worse. Hey, we're bug free, right? Works for me. So this again is why programming with this is is more difficult. Oops. All right, so every time through, except for times I get insanely lucky, I essentially just get a bunch of random values, right? Hey.
Is that one way a program creates random values?
So one question is this a way that programs create random values? And the answer to that is no. They do something much smarter than this. Okay, can anyone think of ways I could fix this, even knowing what we know now?
You do it. This is just put the p thread up there. Just forget about parallelism.
Okay, if I want this to run in parallel still.
Oh.
Yeah, if I don't have parallelism or concurrency, things are easy because it's back to our old life, right? Yep.
I suppose you'd want to sleep, I'm not sure exactly how, but like you want to block or you want to prevent all the other threads from accessing the counter variable while you're working with it,
Yeah.
while using only the stuff we know. So maybe you can just kind of get in there.
Close, yeah.
I don't know if this like works at all, but you could just have them all run independently, count up to 10,000, and then add them at the end after the p join.
Yeah, so if this wasn't such a ridiculous example, that's one good way to do it. So you would make, you could make counter a local variable there so that it's unique to every thread. They could all increment it, so say it was something better than that. And then as part of their return value, they'd have to malloc some space to point to their integer. And then within the join, right, so this would return some pointer to some int. And then within the join, we could actually capture the return value. And then since we wrote the threads, we know it's pointing to an integer. So we could just add everything up from each individual thread in the main thread. And that way we wouldn't have any issue. So that is one good way to do it. And then we'll see more ways next lecture. So any other questions about this? Yep.
How do we do the malloc thing? How do we, so you're saying you create a local variable for the counter to the static int, and then you malloc space and return the pointer? Because it's on the heap, so it's just global then at that point, or what?
Yeah, okay, so we got time, so let's return some values. So my fix, I can say int local count. This is like a very ridiculous thing to do. But let's bear with me. So I'll change counter to be local counter. So now that's on the stack. Each thread, it's all independent now, right? So then I'm incrementing local counter. At the end of this, I'm done. So I could return an integer pointer because I can just cast it to void. I'll call it return. If I malloc, so I'll be nice and say size of int. So now that pointer is in the heap, so if I return that, it's going to still be valid, right? It's not like I'm, oops. Oh, so if I return that, it's still valid. Why is that a compiler error?
Don't worry, semicolon.
Oops, return to. Oh yeah, semicolon 2 and return type. Whatever. Force the issue. Okay. So at that point, it's going to malloc and return, because if we did something like we returned local counter like that, right? That's what we did last time. That's very, very bad, because as soon as the thread's done, that function will be return. It's out of scope. It's some invalid, or it's some kind of trash memory. So we have to use memory. So we'd malloc some space on the stack. Or sorry, yes. So, no, that's good. Feel free to shout at me if I say something stupid. So we allocated some memory on the heap, and then we'd write the value of our local counter there. Yep.
Oh, sorry. When you do malloc here, is it like allocating memory in the threads stack, or?
No, malloc always just allocates on the heap.
Oh, okay.
So luckily for you, the authors of malloc, if multiple threads are calling malloc, they won't fight over each other. So you'll get, if a thread calls malloc, it's going to get a unique block of memory from whatever thread called it. So each thread is going to, because we have 8 threads, there's going to be 8 malloc calls that are all going to be unique addresses, and then each one just returns one address, right? Okay, so now we need to play with the return value. So in join, we of course have to allocate. So this is kind of our return. We just have to allocate some space on the stack to hold our return value, and then we can give the address of the return value. I know it's an int. And then I probably have to void star star. Yeah, whoops. Oh, I need malloc.
Well, would you have to, like, add them up at the end? You have to actually.
Yeah, so I haven't added them up yet. I just had to include the malloc thing. All right, so that gets it. So then return is now a pointer, and then within here I can do counter plus equals dereference ret and add them all up, right?
Will it be free in memory?
That is a good point, and since I am such a nice person, I should also free the memory. So there, that should be what we have. Oh, Jesus. What'd I do? Yeah.
Do you need to pass the void pointer to an integer or something?
I need to cast the void pointer to an integer.
You dereference red.
Yeah.
You never passed it back to an integer. Do you need to do that, or does that not matter?
No, it's an integer pointer.
Oh, what? Oh, I see.
Yeah.
Oh,
What'd I do? Is it consistent? Yikes. Huh, well, that was a crappy example.
The double start, no?
What?
Is there a double start? A double start?
Yes, because it has to be a pointer to a pointer, so it can write the value there. Yeah, what'd I do?
are you adding to it twice by mistake? Like, did you forget to, like, change the counter at the top or something? Or no?
Oh yeah.
No, it's local counter.
It would also be the same every time.
Yeah, it should.
No, it's fine, yeah. That's strange.
Yeah, that's really weird. Oh, of course, local counter is not initialized. Whew. There we go. Okay, I'm not that bad at programming. I'm just forgetful. So 80,000 every single time. Okay, whoever caught that, very, very good. Yeah.
Why did we get those random values in the first one?
So I didn't initialize local counter, so it's just some random garbage.
This one, like the initial implementation, one without malloc.
Oh, okay, yeah. So the question is, the one without malloc, why did I get such random values? And I would have got the random values even in the case where I only had a single CPU. So if I go back, assume I had the rest of the code. So plus plus counter is deceptive. That's a global variable, so that's actually 3 operations. So it has to load that global variable from memory and then to a register or something like that. Then it's going to increment that, and that's going to be local to a thread, and then it's going to have to write that value back out through memory. So you can even get the wrong value if you have 2 threads and you only add to it once. So because there's concurrency, threads can get interrupted at any time and you can't control it. So if the initial value is 0, one thread can go ahead, load that value from memory to a register, which would be 0. Then it could context switch to another thread. That value hasn't changed yet. It would load it from memory, which it would get 0. Then at that point, either thread could execute. They would both increment it to 1, and then they would both write 1 to that memory location. So instead of what we would expect, it writes a 1 and then a 2. It would instead write a 1 and then a 1. So that's the crux of our problem. And we'll get into that next lecture unless I have to do quiz review. Yeah, so just remember, processes, kernel threads enable parallelization. Threads can have, or processes can have multiple threads. We saw a bunch of implementations that probably are valid for the quiz. And then operating system gets some more complexities. And now we have synchronization issues. But hey, we've showed how to solve it at least one way. So just remember, I'm pulling for you. We're all in this together.